So did I get it right this time? Are you guys seeing the preview or the actual slide?
Preview.
There is a way to switch it. Uh, I promise one of these times I will. All right, how's that? Getting there. Okay, Intro to AI Part 2. So this one, we're talking um, less about the AI and more about how AI fits into gaming, particularly serious games. So this is a little bit of a hybrid talk between what Rob was talking about yesterday and AI, and when you might want to use AI in games. So as Rob was talking yesterday, we don't want to fit into the concept of I have a hammer, so everything's a nail. Just because you're using games and serious games does not mean you would want to use AI in it. And so what we'll talk about here is what some of the uses in AI in gaming are, what are some of the cases you'd want to apply it. And it's basically talking about, in the context of gaming, how we may apply what we talked about in the last lecture. Okay, so we're looking at games and AI. We're going to talk about why games are good, what some recent advancements are. We'll talk about traditionally what has been meant by game and AI, particularly the controlling of enemies and other non-player characters and pathing and those things. And then we'll talk about what I mean by games and AI and how you may use AI as a game analysis tool. So why games? Why are they good for stuff? So first of all, reinforcement learning has different data requirements than other kinds of machine learning. As we saw in the previous talk, notably reinforcement learning needs an environment that will allow an agent to act in it and produce what changed in the environment and a reward. Reinforcement learning uses those environments to learn, and games provide those environments. And you don't need labeled truth data for it. Kind of. And I say kind of because when I sit down and play a game, or the agent plays the game, right, you're sort of generating that truth as you go. So I take an action not knowing what the truth will be, and then I get the reward and the new state from it. And that sort of is the truth. And that's what I'm using to learn. So it's true that reinforcement learning doesn't need labeled truth data, but also you're kind of generating it while you're going. And we talked about other techniques and stuff, and those are helpful. There are all sorts of machine learning techniques that are helpful with gaming, although the primary one that we normally see is reinforcement learning. So again, why are games good for certain parts of AI? Well, compared to the real world, games have clarity and rules and a level of simplicity that doesn't exist in the real world. For example, rewards are very well structured and clear. That's not always true in the real world. You may have different competing incentives and different rewards and things in the real world, but in a game, we can really boil it down. So, in a game, we say the score is whether or not you win or lose. You get 1 for winning, -1 for losing, right? That's a very clear, well-structured reward. And it's not usually that clear in the real world. Also, in the real world, we have a much larger action space. In the action space, I just mean the set of all possible actions that I can take. Obviously, in the real world, that number is astronomical. But in a game, you can really narrow it down. For example, for chess, there's a finite number of moves you can make on any given turn. That's your action space. So the actions are well defined, well structured, and they are restricted in complexity. whereas the real world, it's much larger. And the same is true for the state space. For chess, the state space is just where all the pieces are on the board. And again, that's a finite number of possibilities. That's a very large number of possibilities because chess is a complex game. But if you consider tic-tac-toe, within the next 10 or 15 minutes, you could probably write out all of the possible tic-tac-toe states, right? So games help control and restrict and keep the complexity under wraps. That's not normally possible in the real world. Also, the real world runs at one speed. It runs at the speed of time, which I know is relative, and we won't get into the metaphysics of all of that. However, games can run much quicker than that. So I can have a machine running a game that can play 10,000 games of tic-tac-toe within a second. You and I aren't going to be able to play that many tic-tac-toe games in that amount of time in the real world. And we'll see from reinforcement learning, you need to play a lot. You need to explore a lot, and you need lots of reps, lots of repetitions if you're going to learn the right things to do. So being able to move very quickly through the game is very important. And also part of what we'll touch on today, games are very popular for benchmarking reinforcement learning algorithms. So the entire concept of OpenAI Gym, which is one of the Python packages we'll use heavily in this course, that's what OpenAI Gym is all about. OpenAI Gym provides a set of standard environments that people can run reinforcement learning algorithms against and say, well, so a good score on this is if my last 100 plays have been above this score. Well, I achieved that in 300 runs, and someone else's algorithm may have achieved it in 500 runs. And since they're using the same game, you know, hey, I converged on the best score quicker than you, so my reinforcement algorithm is a little bit better than yours. And that's just a simple example, but this is one of the main uses of games and AI. That's not really the focus on this course. In fact, we're turning it on its head. So we're making our custom game environment in hopes of learning something about the thing we're modeling. And then we're using sort of standard baseline algorithms to run against it. So we're sort of doing the opposite of how most people use OpenAI. But benchmarking is one of the popular uses of games in the AI machine learning world. So, you know, if that's true, why do we still have human players at all? And this gets back to what Rob was talking about yesterday. In these really complex systems that have humans in them, it's impossible to fully abstract the human away. And models of human behavior are not very good right now. So in a lot of cases, it hurts you to remove humans completely. Also, the thing you may want to learn about is the human. And if that's the case, removing human altogether and just having AI playing is not the way you want to go. Right? So we have this weird paradigm where we have a game, we could have AI play it, or we could have humans play it, or we can have some mixture of the both. And really, the world that we're going to live in for this course is where we're having a mixture of both. That speaks to one of the points on here is that humans are good for some things, machines are better at other things. And so we're going to try to look and capitalize on the pros of each while avoiding the cons of the other.
So another thing I'll say on that is there's another sort of reason why you might need both is that if you make the model, in this case the game is a model of the domain, it may be simple enough for the AI to solve, but that doesn't mean that the version in the real world is doable by a machine. So, you know, I think about, you know, logistics. So that's carrying resources along transportation networks. It's a very well understood optimization problem. You don't even need anything people would call AI to solve it most of the time. But real world logistics involves all sorts of headaches that have nothing to do with the math of optimizing your flows and making sure things arrive in time. It's like some policy has changed, or there's some political a rule about what you're allowed to fly over what country, and that rule has changed, or your plane broke down in a way that you've never seen before, and your model didn't predict, and you have to reroute it on the fly, and you can't get through to the airport you'd normally use. You know, all these things that humans are good at sort of problems and solving that you'd never list in advance. You couldn't possibly list all these factors in advance for the machine to learn. The machine can do the mathematically hard part, which is figure out what the optimal flow is, but you still need a human to execute it in real time or oversee it. And as a result, since you're going to have the human execution time, you'd better account for the human during analysis time. Build plans that the human will be able to fix, not just plans that would be optimal if nothing ever goes wrong. And so it's very tempting to assume that you will automate everything. And sometimes that is not even remotely feasible with current machines because it is so hard to, because the world has so many things the machine doesn't even know about. But
yeah,
humans are bad at math in general, especially bad at probability and uncertainty. And so you don't just want to throw the humans out and says, well, machines can't do this, so we'll just have humans do it. That's also bad.
Yep, and the last bullet here just highlights some, out of the box use cases where you would want to use sort of machine learning in games. So one of them is to jumpstart machine learning algorithms. So that could be providing a little bit of truth data so that you can do semi-supervised learning that we talked about. Or in fact, you could use the game to just generate the data that you're going to use for your model. There's a lot of caveats there. You have to be very careful. But we do have some research where that's done. And also you could set up a game around existing data to help get it labeled correctly. So it could be used as a mechanism for generating those truth labels for your data. There's a lot of different uses. We'll mainly focus on sort of what Rob was highlighting. We want to learn about the human in this course, and we're going to keep the human in the loop to do what the human is good at, which is to use their intuition and their decision making. And we will use machines to do what the machine is good at, which is to crunch a bunch of raw numbers that humans aren't capable of doing, as well as the machine. So moving forward, these are some of my favorite examples of recent accomplishments of the world of AI, machine learning, and games. Obviously, there's Google's DeepMind, which if you're not following in any kind of way and you're interested in this sort of stuff, you should really think about following them, because they started out with, Atari learning, which basically looks at each pixel as the state. So the state of a chessboard is where all the pieces are. State for an Atari game is just all the pixels. And they learned how to play Atari games with superhuman performance. That's where sort of DeepMind kind of started. And they've been now moving beyond pixels into these more abstract spaces. My favorite example is Hanabi, which we won't really get into, but it's a fun little cooperative game with hidden information and conventions. The basics, we're trying to play different tiles. I can't see my tiles, but I can see everyone else's. And what I'm able to communicate to other people is limited. And so that sort of cooperation is very hard to learn. And that's sort of what's being tackled now. There's people working on StarCraft, teaching the computer how to play StarCraft. Same thing with poker, which there are some claims that for some limited poker games, there are reinforcement learning agents, which are just trained up pieces of software that can play poker better than humans. One of the latest things is the game Diplomacy. So there's some people trying to use machine learning to figure out how to get a computer to play Diplomacy best. Usually they're focused on finding optimal play and what the best strategies are and being able to outperform humans. But there's also a notion of testing the bounds of a game, which is if you're familiar with some of DeepMind's work in the chess and Go world, they have Alpha, Zero, and these other things where they learn completely off of playing against themselves. And so you're really learning the bounds of the game and what's possible in the game in ways that you don't get sort of with humans doing it. Again, we talked about augmenting data sets to improve supervised learning. What most people are probably familiar with for AI in games is realistic opponents. However, there's ways to progress in that too, so that war games have more realistic and crafty adversaries and those sort of things. And of course, one of my favorites is decision support algorithms, which are basically things that make recommendations to humans. So if I'm doing a task and I have a decision support algorithm helping me, it's looking at the world, seeing what's happening. It's trying to predict what my best actions would be, and it makes recommendations to me. Hey, you should maybe think about doing this. And I say, oh, yeah, or no, I don't really believe you. I'm going to stick to my guns anyway. And then so those are some of my favorite kind of systems. And these are sort of, some of the fields that you can get into if this is interesting to you. That's not quite serious gaming. But this is certainly one of the stronger research directions for game and AI. Again, it's not quite what we'll be doing in the course, which I'll get to in the next couple of slides. So recent advances, again, so on the right is actually a map of how they're encoding certain things for the game of diplomacy. If you don't know the game of diplomacy, don't worry about it, it's okay. Just an example here. To show you some sort of cool stuff that's happening out there. Basically, they have to find a way to represent it so that the machine can understand what's happening and take actions, and that's what I'm showing over there. Some of the more recent ideas for reinforcement learning that involve games that are a little bit different are shown on this slide, and these are some pretty interesting concepts. I won't get too much into the detail. Most of the games we talk about, like chess, are zero sum. And by that, it's a game theory statement definition in which you have two players in a zero sum game normally, and if one player wins, the other player must lose. So there is no win-win situation in a zero sum game. So for chess is not quite zero. Well, chess is zero sum. Because if we draw, we both get zero. We both get the same. And if I win, you lose. That's just a theory, a game theory. Yes, I do follow that YouTube channel. Another example is human-machine teaming and collaborative robotics. There's a lot of research that goes into teaming and how teaming in general. So how humans team with humans. There's a lot of active research, and there's also a lot of research into a mixed team, which is humans and machines working together. And there are ways that games can help you get at that. One of the more interesting takes is running cognitive experiments using games. So can I test different concepts like human factors concepts? An example might be, can I sort of gamify tutorials and things so that software can teach you how to use it while you're using it? So that's sort of what in situ means, is in place. Another one might be, testing cognitive load, cognitive burden, boredom, stress, these sort of things. There's an entire field of research called affective computing that looks into these things. So there's definitely a lot of interesting angles that you could take gaming and different machine learning concepts that aren't necessarily serious games. So what I'm showing you here is that what we're doing in the course, while it is AI in games, there's a lot more that you could do with games and AI than what we're doing, right? So I'm just trying to give some exposure to that. Now looking back and saying, well, how has AI traditionally been used in games that you may have played? Well, it's usually governing the actions of non-playable characters, right? And it's usually enemies and how they attack you and how they might path. But it's also things, like the villagers and things like that in Minecraft. Oh, yes, we've heard of this game. But some of the algorithms that you will undoubtedly learn if you take an algorithms class are pathfinding algorithms or planning algorithms. So you'll learn about things like A-star and Dijkstra's algorithm, things like that, the Bellman equations for dynamic programming. A lot of that is used to figure out how to get from point A to point B in the best way possible. So you see some of the popular methods that have been used for doing this with NPCs. There's Monte Carlo tree search, which is basically a tree structure lookup table that you can expand different branches of the tree based on metrics. You may not be able to enumerate the entire space with a tree because it might be too big, but Monte Carlo tree search can help you only go down the branches of the tree that are most important to go down. You have pathfinding algorithms that are mostly based on Dijkstra's algorithm. So A-star is an extension of that, and there are other ways of pathfinding as well. You know, NPCs that you interact with are usually governed by state machines, usually finite state machines, which is kind of one of the structures of our game that you'll see in the zombie or flu game, in that you have a number of states that you can be in and then transition probabilities between states so that I may move from one state to another state, etc. And lastly, there's a whole host of composer systems, which are basically conditional scripting of when AI does things. So if you've ever played tower defense games or any kind of games like that, you see these sort of composer systems, which basically operate on timing and other conditionals to throw enemies at you, to spawn enemies in, and these sort of things. So, again, this shows some of those things. So we have in the upper right is pathfinding. So this is an implementation of A-star, where I'm trying to find a path from the blue dot to the red dot. And the white shows what I'm exploring. So I kind of have to explore everything. And then once I explore through stuff, I can find my way back. Finite state machines down in the lower right. It's the ghost behavior for Pac-Man implemented in a finite state machine. And right below in the lower left is conceptually how Monte Carlo tree search goes. So again, we provide these mostly, for historic conceptual purposes. It's likely that a lot of people, when they hear serious games and AI, they think we're just making something smarter like this. But that's not really what we're doing. So I provide this here for the context of, this is what a lot of people mean when we say games and AI. So I'll pause for questions before I move into the meat of the lecture, which is serious games and AI. Okay, so what we mean by games and AI, what this course will focus on, really is using these AI or machine learning techniques to analyze our game and our game data. Right, so we can generate some game data, and there's a whole host of analyses we can run on it, from statistical models to clustering and all of those things. And we can also use reinforcement learning to analyze our game. That's really what we'll talk about for this course. So our focus, we're going to use AI as an analysis tool. We're not developing the AIs for the game, sort of how traditionally it goes. And we're not coming up with a new way of governing NPCs or something for entertainment purposes. It's really an analysis tool. And we'll talk about how games fit into the research process, which is driven by a research question and a hypothesis. And from there, you can ask yourself, if that's what I'm trying to research and that's what my intuition based on what I've observed is, what data do I need to collect to prove that or disprove it? And games can be a good way of getting that data, particularly if there's a human aspect of the research, particularly human decision making. And then we're going to use all of these tools that we talked about to analyze the data and the game to help us answer the research question, right? So when we say games and AI for the course, this is what we're driving to. And again, we don't want to fit it, get into this hammer and nail kind of situation where if I'm using a serious game, I must come up with some AI thing to put in it. That's not always true. What I've done is I've outlined here some of this is not an exhaustive list, but it is certainly some of the more popular use cases for when you'd want to use machine learning with a game. And these are if you want to quote unquote solving the game, which is kind of what DeepMind has done with chess and Go and all these other things. They're really trying to find out what the optimal or better than human way of playing the game is. Related to that is finding new strategies, which doesn't always align with the first one because they might just be executing the same strategies but better to solve the game. You can use machine learning to find novel strategies or strategies you didn't expect. And Rob mentioned, we sort of saw that in the Hivelet example that he talked about yesterday. We enumerated some strategies that we thought we'd see, and then through analyzing the gameplay data and talking with the subjects, we found that there were new strategies that we didn't anticipate at all. And finally, you can find errors in your models, which we'll talk about. Basically, if you find a degenerate strategy, like you should never do anything, and if never doing anything gives you the right score and that doesn't match reality, that might show you that you have some problem with your game model that you need to change. So these are definitely popular use cases, but they're certainly not all of them. Rob talked about some of these yesterday as well. So I'm going to use this Atari example for when I talk about solving the game. While people use it for many different things, in this context, we'll say that it's typically finding optimal strategies. And I will note that optimal here usually has a strict mathematical definition of optimal. It's impossible to do better. It's the best you can do. In this sense, we mean that. However, there are times when we say optimal and we mean it a little bit more loosely, in which case it's the best that we found so far. Right? There might be something better out there, but we can't find it because in a lot of these cases, what's optimal is not provable, right? And there's a whole set of mathematics that sort of govern complexity and what's provable and what's not provable. Which we won't get into that. But there's a class of problems, non-polynomial, NP complete, NP hard kind of stuff, where we may not be able to prove optimality, but we certainly want to find the best we can find. And that's often what we mean by solving the game. And this helps us provide baselines, right? So we can say the best that we've ever found is this. And so we can say, well, my algorithm takes half as much time, but gets me within 2% of what sort of the optimal is, right? So that's very helpful if you want to provide these sort of baselines on what your algorithm is. And what we're trying to get at is superhuman performance. And we see that with Atari. The reinforcement learning agent has learned to play this game better than any human could. And it's just phenomenal what it can do, really pushes the bounds of the game. Any questions on this before we move forward? So there is a little bit of flavor for this for the course. So we have our game and we have a reinforcement learning agent that we've trained up. We haven't trained it all the way, so we're not really solving it. However, we are trying to set a baseline and come up with what a pretty good strategy is, and that's what we're trying to do. So, when you play the game, there's so many options, you don't really know it's good. But if we train up a reinforcement learning algorithm, we can kind of get a baseline, right? So there's a little flavor of this in the course. Rob, did you have something?
I wasn't sure if you wanted to talk about the concept of local optimality versus global optimality.
Yeah, so that's a good point. So local and global optimality. In my mind, it's both something that's very simple, but also something that could be very tricky. And I know that may not make sense, but it might be best if I try to do a white. Well, if I'm afraid if I try to go into a whiteboard, I won't get the slides back. So local optimality. So if you imagine a curve that sort of goes like this, right? You sort of had one peak here and another peak here. So we say that this is a local optima because all the points around it are worse. And you kind of have to get far away from it before it starts to go better, right? So you may get trapped in that local optima where you try to explore around it, but everywhere around it is worse. So you stick to it thinking that you're in the best optimal spot. Where, however, if you were able to explore all the way over here, you would find something better, right? So if this is the whole graph, we would say this is the global optima because across everywhere, it is the best. And we would say this is a local optima because around it, nothing else is better. And the trick is you may get stuck in that local optima and may not be able to flash. It may not be able to work your way out of it. So AI solved checkers is pretty cool. Yes, I agree. There's a lot of good videos on that. If you want to see what superhuman checkers performance is, if you want to always lose at checkers. Relative max versus absolute max. Yeah, exactly. Just different names for it. So relative max, absolute max, relative min, absolute min. For games that are based somewhat on things like human reaction time, how do you find the best strategy that is feasible for humans? So this comes up, so if we're solving a game like Atari and we want to include something like human reaction times, sort of to make it fair, this has been studied quite a bit in the StarCraft world. And what you do is you constrain your actions. So you would limit the number of actions per second, and you would limit the number of actions per minute. And those are two different constraints and two different limits that keeps the computer from cheating. And it keeps the computer from acting and behaving in a more efficient manner than humans are capable of. Right? So you can build in those constraints in your reinforcement learning model, into your reinforcement learning agent, to follow the same sort of constraints that humans have, right? So that's one way you could do that. That answered the question, Vivian? Okay. The next thing is finding interesting strategies. So we see this a lot in the chess world. I play a lot of chess. I follow a lot of chess. So I'm sorry if that's what, a lot of the examples are. However, there are a number of chess engines that play much more strongly than humans do. And so when the machines have tournaments against each other, you get some really interesting things happening that humans are like, why did they do that? What's that about, right? And there's actually a number of new chess strategies that have come out of machine play. And you'll see it if you watch some analysis channels. You'll see like, well, that was a very Leela move, or that was a very AlphaZero move, right? Or that was, a very stockfish kind of thing to do, right? And one of the examples of that is pushing your outer pawns up very quickly and capturing that space, which is something that AlphaZero learned and really likes to do. And so when you see players who would not normally have pushed A, B, or G and H pawns as early, people are starting to push those a lot faster now, grabbing that space in ways they didn't do before. That's a new interesting strategy that we only got from having AI play, right? And I also included down in the lower right a picture of hide and seek, which was something that came out recently that was very cool. They basically didn't really give them any hints on what hide and seek was. They basically just said, you can't be detected. The blue players can't be detected by red players and those sort of things. And they allowed the players to move around these things in the environment to block views and things. And they learned a number of very interesting strategies. One of them was degenerate, which means it's not really good to follow that, and it doesn't really make a lot of sense to do in the real world. For example, if the playboard is unbounded, it's infinite in all directions, the best strategy to do if you're a hider is just to start running away, because you have infinite stamina and everyone runs at the same speed. So if I get enough of a head start on you and I just keep running in the same direction, you'll never be able to catch up to find me, right? And now that's not really learning hide and seek, because what they really wanted to have them learn to do is to use these ramps and blocks and things. And so that's an example of a degenerate strategy that was found, but it was also very interesting. All right, so some questions. What about something like a shooter that involves mechanical skill? So again, you could build those constraints into your model. You can build in shot variants, for example. So you can say, well, top tier humans have an accuracy of around 80%, and their spread is normally around this big. And so you can program that in. You can program that limitation in. So if the machine means to shoot there, you can build in that spread and figure out where it's actually going to shoot. So there's a number of ways that you can restrict, constrain, and limit these models so that they are behaving in accordance with human play. Isn't the idea behind a task that they can do strategies that a human lacks mechanical skills to pull off? Yeah, so in the speed running world, which is another thing that I really like and follow, it's very interesting to me. You have these, human speed runs, which a human is playing, trying to get the best time, but you also have tasks, which is a tool assisted speed run, which is basically you can program in each frame of the game what buttons you want to have pressed. So you can do frame perfect movements. And that does make it possible to play better than a human could play, not because the inputs restrict it, but because humans are not good at hitting a button in a particular, 1/59th or 1/60th of a second, whereas a machine can do that reliably every time. A company called DeepMind had actually created an AI. Yeah, thanks, Athi. So I had mentioned DeepMind earlier. If you're interested in this, if this has captured your attention and you have not looked into DeepMind, please do. They have very interesting research. They have really good public relations people who put out very understandable, very digestible, readable blogs. So definitely check them out if you haven't. And yeah, so they have first-person shooter games that DeepMind's working on, and also the RTS games, the real-time strategy as well. Question: how would you train an agent for a 2-player game if it's better than a human who controls the second player? That's a very loaded question. So there is reinforcement learning algorithms called multi-agent reinforcement learning algorithms. The acronym for that is MARL, M-A-R-L. And you can look that up. It's basically extending traditional reinforcement learning algorithms to handle multiple agents. And there's a number of different paradigms and schools of thought on how to do that. For example, those multiple agents can share one mind, so they can jointly plan. or thank you, Rob. Or they could be completely in isolation, and you can control what information is shared between them. There's a whole host of possibilities there. And if they're playing better than human, who controls the second player? It really depends on what you're trying to get out of it and what you're trying to research. So I hate to say it depends to your answer, but it really does depend on what you're doing. If you're trying to solve the game for a multiplayer cooperative game, you may want to have machines playing all of the roles. If you are interested in how humans and machines team together, you would want one of the players to be a machine, an RL agent, and you would want the other one to be a human. If you want to figure out how humans do and compare humans to how machines might play, you may want to play some of both. Some where it's only humans, some where it's different mixtures. So it really does depend. And yes, MARL does stand for multi-agent reinforcement learning. We will not use multi-agent reinforcement learning in this course. Well, I say that out of the box we won't. So the base game is a one-person turn-based game. If your game mod adds in additional players, then you have the ability to start using some MARL. Finally, finding modeling errors. So we've touched on this a couple times. I'll breeze over this. For example, the hide and seek degenerate strategy in the lower right of always running away. That's a modeling error. Because people don't have infinite stamina. Not everyone runs at the same speed. And if you're a hider, if you just run away in the same direction, you're probably going to get tired. You may get caught. It's not always a winning strategy. So that exposed an error in the underlying model. We've also seen this in some of our own games. So Rob mentioned yesterday that game that we did for emergency responders that was about a nuclear device detonating in a city and how you would respond to it. So they used a machine learning technique called Monte Carlo tree search on that to figure out what some good strategies are. And they actually found a degenerate strategy. And then because of that, they were able to fix those errors in the model and have the model be a better representation of reality. Rob, maybe a word or two on that. And I think.
Yeah, I mean, so in particular, in that case, our mistake was in our scoring, where we were trying to incentivize the right behavior. And so we gave you some reward for people who survived, and we gave you some penalty for people who didn't survive, and some penalty for people who survived with injuries. And we gave you a reward for evacuating people out of the danger zone. And it turned out that the machine came back and said, the correct answer is to evacuate everyone who is easy to evacuate, which is also the people who need no help, out of the danger zone, and completely ignore all of the people who are at risk. This was not a credible strategy, and when we lowered the reward for evacuation, this went away. We still left in some reward for it, so you got some reward for removing people entirely from the area. And that's a case where, I mean, there's always a problem with any model. When you build a model and it tells you something that you didn't expect, you have to figure out if it's a surprising result that you should learn something from, or if it's a degenerate result that you should fix. And that's subtle, because if you reject all of the novel results, then you'll never learn anything that you didn't already know. And if you accept all the weird results, then you'll get ridiculous things from ridiculous models and believe them. And so there's a lot of work on how do you validate a model on other data that you do know, or in our case, we showed this game to experts and asked them, does this feel like your job? Or here's a strategy we found, does this sound credible? As a qualitative kind of evaluation. In other cases, where if you're in a more data-rich environment, you would run it on a known historical case study and see if it gives you the result that you knew it should have done. And then when it gives you a weird result in a future case, you have some reason to believe that that's a useful learning result rather than a degeneracy result. But
Yep.
all models are wrong. Some models are useful.
Yeah. So just to highlight something that you'll come across when you get your hands on this game and you play it a couple of times. The game is not necessarily optimally balanced, right? And so you may want to explore some of these techniques to see if there are any degeneracies and any incorrectness for the models of the game that we have, right? So there's definitely some interesting things here that you could look in, that you could use these concepts into the game we built. Some of that's on purpose, some of that may not be on purpose. We'll see. So I think that's all that I have for this one. I think that's the end of it. I think we're moving into, until 11:30, we have question and answer, which we'll stick around on the Zoom for. I'll open it up to the instructors first to see if they have any questions or comments on the material. And I think we'll stop our recording, Michael, for the question and answer. Unless Amna thinks we should record it.
I think she said she had to go earlier.
Okay.
Yeah.
So,
I would turn it off for the turn it off for the discussion. I think that's right.
Okay. So let's
it's also important that we squeeze in the mathematical puzzler.
Yes. All right. So let's stop the recording. I'll stop sharing. We'll move into question and answers.